Welcome all of you. Today I'm going to discuss Arnold cell problem. Okay, so Arnold cell is basically used for finding the diffusivity of a liquid. Okay, so we can put any liquid here. So right now you can see this is water. Okay, and then you measure the diffusivity path. Diffusivity path is this in this case, and find the diffusivity. How we'll discuss now. So in this problem you can read uh, time is given time what will be the level after t equal to 10 hours. So this is the level right now you can see, and the water surface was 7.4 centimeter from the top. So this is basically 7.4 centimeter. Okay, and now you have to find what will be the level after 10 hours. So we'll apply the concept of pseudo steady state in this case. Okay, uh, vapor pressure is given at the surface, so that will be used to find the concentration mole fraction at surface. So I will solve this from a scratch. Okay, it may take some time. We'll do some mathematics. If you are interested in direct equations, okay, I will highlight the equations we are going to get. Okay, the flux and time equation for time later. So just be patient with me and try to follow with me. uh, so for us, okay, z start from here. So this is the z direction. Okay, this is z equal to 0 0, and then we have right now the boundaries z1 and z2. Okay, starting from the scratch, as I told you, from differential equation, this is one dimensional diffusion, isn't it? Z. So you will, what will get, dna over dz is 0, right? There's no flux in x and y direction. So that gives me NAZ, we can say NAZ is constant. Derivative of any constant is 0. So NAZ is 0. So what information, how it helps? When we integrate over the z path, z length, z, we can take NAZ out because it is constant. Okay. So this will be used later. NAZ is constant. Now, as usual, okay, let's go to the fixed law. NAZ equals minus C DAB DYA over DZ plus the YA NA plus NB. Okay, we have A is water, B is air. Now, this air is stagnant, it's not moving. So we are saying that this is unimolecular diffusion. So only A, the water is diffusing in air. So NB has to be 0. Okay. Now NB is 0. So just try to solve for flux NAZ. How we do that? So NAZ is here. So NAZ 1 minus YA. Okay. This YA I'm taking. YANA equals to minus C DAB dya over dz. Okay, so if we integrate this one, dya, so dya, let us separate the variables. We are solving differential equation, we are applying variable separable method, and then what we have, dya over 1 minus a, and then we have dz. Okay, and dz is constant, and we will have, okay, so what else we have now here? NAZ over CDAB, and we have minus sign here. So now what we'll do, we need to integrate, okay. NAZ, okay, NAZ I have taken it outside, so this is important, okay. Just I just jump to one step. So this NAZ is here, okay. NAZ and DZ. So this NAZ, we got it constant, isn't it? NAZ is constant. So we can take this outside, okay. So we can take this outside, then it's basically dy over 1 minus ya equals NAZ divided by CDAB dz. Okay, z, now we will integrate over the diffusion path, okay, that is z equal to z1 to z equal to z2. So this is the diffusion path, diffusion taking place at this point, okay. So z1 to z2, so this is z1 to z2, and then ya1 at z1 and to ya2. So that becomes ln, if you integrate this one, this is ln ya with minus, okay, and ya1 to ya2, and we have equal NAZ CDAB. Here also we have a minus sign, so that becomes Z2 minus Z1, okay. So minus sign, both side it will go, and then what we have, ln, we apply the limits, ln 1 minus ya1 minus ln 1 minus ya2 equals NAZ divided by CDAB, and Z2 minus Z1. Z2 minus Z1 is the diffusion path, okay. So usually we represent with this capital Z, that is Z2 minus Z1. So now the flux NAZ is 1 minus ya1, that is basically yb1. So we can write it here, ln yb1, okay. Sorry, ya2, ya2, this should be ya2 minus ya1, okay. So ln yb2 minus ln yb1, okay, whole, so divided by z, okay, and then you have CDAB in the top, okay. So this is the equation, we got it, NAZ equals CDAB over Z. Z is the diffusion path, okay, from the top. So again, please be careful, this is Z, capital Z, okay. So now with the diffusion taking place, this height will be decreasing, water will go down, so that will increase. Okay, that will increase. So now our equation, take this from C dAB over Z ln yb2 minus yb1. Okay, so ln yb2, this is C ln m minus ln n equals L of m divided by n. Okay, so that's basically, this is the equation. Again I will write C total concentration you can find by P over RT ln yb2 yb1. Okay, now in this question, if you see, uh, it's asking also to find the mass transfer coefficient. Finding the mass transfer coefficient. So how to get the mass transfer coefficient here? Flux is, as we know, flux is proportional to concentration difference. So basically, Ya1 minus Ya2. Ya1 at the surface, at the interface, and Ya2 in the bulk. So that's the difference of concentration. So somehow we have to rearrange this equation and write in terms of Ya1 minus Ya2. Okay, so if you rearrange this equation, you can make it. Okay, I will skip the steps. Okay, so that's, we can make it Ya1 minus Ya2 divided by, so if you you can take this down, and we what I have done, I have multiply with Ya1 minus Ya2. Okay, let me do it. So Ya1 minus Ya2, and that will come down ln yb2 minus yb1. So that's interesting. See here, NAZ is CDAB. We need one more step. So that's our driving force, Ya1 minus Ya2 divided by this one. Again, this is B in term of B. So this one also we can do it in term of V. I can rearrange this such that that become one. Okay, you can see 1 minus Ya2 minus 1 minus Ya1, that is becoming Ya1 minus Ya2. This is just mathematics. As engineer, you should not try to escape the math. Okay, do all this calculation, this manipulation, you feel confident about what you are learning. So this is again, this is yb2. So this is yb2 minus yb1 divided by ln yb2 yb1, and this one is called log mean average, log mean of yb2 and yb1. So this is CDAB. Yeah, this Z I have missed. Okay, Z again is the diffusion path, measuring the height from the top, height of the liquid from the top. So that's Ya1 minus Ya2 divided by YB log mean, ln mean. Okay, so these all are constant. NAZ is proportional to Ya minus Ya1 minus Ya2. So this basically your this term becomes mass transfer coefficient. That's become Kc. Okay. So now what we have done, we have derived the equation for the flux. Okay, for the flux that is diffusing into air, and we have relation with the z. Z is the diffusion path. So now we will be using pseudo steady state concept to will make the balance, mass balance, and then z is variable now here. Z will be z from the top, it will be increasing. So z is diffusion path from measured from the top. Okay, this is the this from the top. So as we move, as diffusion take place, this level of water will be going down. So that capital Z is will be increasing. Okay. So in this problem, uh, we need to find the height after 10 hour. It could be otherwise. So find the time required so that the new height is this. New diffusion path is this. Okay, the Z. Or sometimes it could be uh, you have the time, you have the height, and then you need to find the diffusivity. But in this case, DAB is given to you. Okay. So now we what we do, we apply the mass balance. Okay, at this. So there is nothing in, only out. So out is the flux. This flux is going by flux, right? So flux is a mole per unit area per unit time. So if we multiply flux with area, that gives you mole, isn't it? So we have Na. So Na times area, that's become mole rate, the mole per unit time, mole of liquid living per unit time. So this is mole. If you multiply with the molecular weight, that become mass. Okay, that become mass, and then this becomes mass of the liquid living. So d per second per time. So that is basically equal to dm over dt. Okay, d mass dm over dt. So mass living mass is what? Volume times density. Volume of the liquid times density of the liquid. So density is constant, and then volume dv. Okay, let's take one more step. dv over dt, and then what we have, the volume is area times height, right? Volume is area times height, area of the base times height in the liquid. So now we apply the mass balance. In is nothing, right? In minus out, so 0 minus this is this. So rho d over dt of volume A area times z, the small z. Okay, a small z is the height of the liquid. Okay, so flux Na times A times molecular weight is rho. A will come outside, and then d over dt. Now uh, the z the z is the height of the liquid, right? So we need to we'll be measuring the diffusion path. We'll be measuring the from top, the height of the from here. We'll measuring height from here to here. This small z is this height. Okay, so we have to replace this in term of capital Z from this height. So what we can do, our z small z is basically uh, total length minus the diffusion path. Okay, so dz over dt, L is constant, total length is constant, basically gives you minus dz over dt. So this is okay, L minus z, and we have minus here. Okay, so that becomes dz over dt. So again, area, we can cancel area. Okay, so what we have, Na times molecular weight equal to density and then dz over dt. Then we will have negative side, both side, so it will also get cancelled. Now the flux was, so we can have mw over rho, and then flux, what was the flux? Flux was c dab. This is capital Z. Okay, we have to be careful. Where capital Z, yb log mean. Okay, this is the flux Na, and now equal to dz over dt. Okay, we are almost done. So dt. So now we do variable, separation of variable. Dt equal is constant. Okay, mw, wait, not mw, rho. So dt will be rho divided by mw. Okay, dt rho yb, yb log mean, we have z, so z dz, and then divided by c dab. So we integrate z. Okay, so if we assume that initially time is 0, t equal to 0 to t. Okay, then z1 to z2, capital Z1 to Z2. So that's the equation. We got it here, t equals rho yb ln mean divided by mw c dab, and then multiply by z dz. So that becomes basically z square, right? Z square from z1 to z2. So your time, okay, t required to make the level, the diffusion path from z1 to z2 is basically this one, rho divided by molecular weight yb log mean and c dab z2 square minus z1 square divided by 2. Okay, so this is the equation. If you have the equation, you can use it directly. C dab, and this multiplies z2 square minus z1 square. Rho is the density of liquid. MW is the molecular weight of liquid. YB ln mean you will find. Okay, how? From YA1 to YA2. YA1, how we find? By vapor pressure given. So PA, vapor pressure divided by total pressure. YA2 in this case, we had the blower and the top, so it is taking away everything. So A is not present at the top of the cell. Okay, at the top air is going like this. So where at the top YA2 is 0. Normally it's like this. So YA2 is 0. This value, vapor pressure is given. Vapor pressure is given 233 mg. Is total 1 atmosphere. So YA will be 233 divided by 760. So you know YA1, YA2, you can get a YB. From here you can get YB1, right? YB1, 1 minus YA1, same YB2. And then so you can get log mean YB, which is nothing but YB2 minus YB1 divided by ln. Okay, so this equation is important. So what we got it by log derivation. Hope this is clear to you. So if even if you have equation, you can use it. So Z2 is the path. So initially it was 7.4. Okay, so Z1 in this case is 7.4 from the top. Okay, Z1 is 7.4. Time given is 10 hour. DAB is given. YB log mean you can calculate. Density of the liquid and molecular weight of the liquid. You can find the Z2. Okay, so this equation is very important. It can be used in many ways. So sometimes time is given for you. Time in making means from Z to Z1. So Z2 is given, Z1 is given. You can find DAB. Okay, DAB is given and Z2 and Z1 is given. What will the diffusion path, initial and final, what time it will take? You can calculate using this equation. Okay, hope this is clear. You like it. Let me know if you have any question. Okay, thank you.